In the last lesson, you were introduced to the carbonyl group, which is one of the most electrophilic functional groups in all of organic chemistry. Because it's so electrophilic, nucleophilic additions to the carbonyl group will constitute one of the most important reaction classes with this group of substrates. Just to remind you, an addition reaction is one in which an XY bond adds across a pi bond to give a product with two new single bonds and the pi bond broken. In the context of carbonyl chemistry, oftentimes Y will be a hydrogen atom and X will be some nucleophilic atom, which adds into the carbonyl group. Before we can discuss addition to the carbonyl group in great detail, we need to take a look at a new elementary step, AD sub N. AD sub N is the addition of a nucleophile across a polarized pi bond with the formation of a nucleophile carbon bond. The curved arrows for this process are drawn here. You can see that the nucleophile is the electron source, donates its electrons into the pi star of the polarized pi bond, and electrons from the pi bond are kicked up to the more electronegative oxygen atom. From these arrows, we can see that this process is an N to pi star type interaction involving an N orbital on the nucleophile and a pi star on the electrophile. The carbonyl group has one of the lowest lying pi stars in all of organic chemistry due to the high electronegativity of the oxygen atom, and so this process is very easy for most carbonyl groups. In the product that results, the negative charge that was on the nucleophile has been transferred to the oxygen atom of the carbonyl, and we've generated a functional group called an alkoxide. After treatment of an alkoxide with some proton source, we generate an alcohol as the ultimate final product of direct addition to carbonyl groups. There are two mechanistic pathways for the addition of nucleophiles to carbonyl groups. Depending on the conditions, whether they're acidic or basic, one of these two pathways will be followed. Both pathways are referred to as the AdN2 type pathways because the addition of the nucleophile, which is a bimolecular step, is the rate-determining step in both cases. Under basic conditions, in which the nucleophile is typically a very strong nucleophile, addition to the carbonyl group will happen before protonation and will generate the alkoxide intermediate that you saw on the last slide through an AdN type addition to generate this alkoxide intermediate. Then, after the addition of some proton source externally by the chemist, will generate the final alcohol product. Under acidic conditions, protonation of the carbonyl group happens first, usually because the nucleophile that's added in is too weak of a nucleophile to add to the bare carbonyl group alone. Treatment of the carbonyl with a proton leads to protonation on the carbonyl oxygen, the most basic site in the carbonyl group, and then, after lowering of the LUMO due to protonation, the nucleophile is able to add into the carbonyl group to form the familiar alcohol product. In the next webcast, we'll take a look at some real-life examples of addition to carbonyl groups and survey the kind of nucleophiles you'll encounter that can add to the carbonyl group to form alcohols.